Okay, let's talk about Archimedes' principle, or principle of buoyancy. Um, we talked previously, and you know that when an object is submerged in a fluid, there tends to be a net upwards force acting on it. We also know that pressure increases as you go deeper into a fluid due to the weight of the fluid that is on top of you. So let's investigate these things and see if we can put them together. So consider the cylinder of liquid that we had previously, and now consider that we have some cylindrical piece of material that is in the middle of it. And the cylindrical piece of material has straight walls with a base area of A and a top area of A as well. And now let's say here also, for simplicity, that the atmospheric pressure above the liquid level is equal to 0. P naught is equal to 0. And so we can say that the pressure at the top of this, I'll call this pressure 1 at the top and pressure 2 at the bottom. We'll say that pressure 1 is equal to P naught plus density times gravity times height 1. But P naught is equal to 0. So P1 is just equal to density times gravity times height 1. And then similarly, P2 goes down to height H2. So P2 is going to be density times gravity times height 2. Okay, so we're trying to investigate this buoyant force. And the buoyant force is the net force upwards. It's going to be, we know there's a force F2 going up and force F1 going down. The buoyant force is the difference between these. So now that we have the pressures and we have the area A, we can actually say here, because force is pressure times area, force 1 would be pressure 1 times area. So this is density times gravity times height 1 times area. And force 2 would be pressure 2 times area, which would be density times gravity times height 2 times area. So that's force 1 and force 2. The buoyant force is the net force between them, or the difference of the net upward force. So it's the difference between them. And so our buoyant force, which is F2 minus F1, and this is the net upward force, and that's why we took the upward direction to be positive. That's why we said F2 is up. So this is going to be density times gravity times height 2 times area minus density times gravity times height 1 times area. By the way, this is density of the fluid, right? Because it's the pressure in the fluid. Okay, so we'll look at this, and we actually, density of the fluid, gravity, and area are all constants. We can factor these out of these. So the buoyant force is going to be, factoring this stuff out, we're going to have density times gravity times area times height 2 minus height 1, or depth 2 minus depth 1. And if we look at this, this would be H2 minus H1. Remember that we call for a pressure increase due to depth. H is positive on its way down, so this would be a positive quantity, H2 minus H1. And it is the height of this cylinder that we have in here. So basically, and this area is the area of the cylinder. So what we have is this buoyant force is density times gravity times I'll call this the area of the cylinder, times the height of the cylinder. But the area of the height, or the area of the cylinder times the height of the cylinder, this would be the volume of the cylinder. So the buoyant force would be equal to density times gravity times the volume of the cylinder. And to generalize this a little bit more, it's not just the volume of the cylinder. The cylinder is the object that's in the fluid. So we can actually say, to make it a little bit more general, the buoyant force is equal to the density of the fluid times gravity times the volume of the liquid displaced. So say volume displaced by the object which is in the fluid. So this is actually a very important key point later. If it's fully submerged, the volume displaced is the volume of the object. If it's only partially submerged, let's say that you have something over here. Here's your liquid level. Then if it's only partially submerged, then your buoyant force is only related to this volume, which is submerged. So it's very important that it's just the volume of fluid which is displaced. So this is the buoyant force. This is Archimedes' principle. So there's one way to say it. The buoyant force is the density times gravity times the volume of the displaced fluid, and this is the density of the fluid. We could take it a step further here, though, still, because remember that density is equal to mass per volume. So then we could say the density of the fluid would be equal to the mass of the fluid divided by the volume of the fluid, right? The volume of the fluid displaced. So we could also say then, therefore, the volume times the density would be equal to the mass. And so we have here the buoyant force, rearranging, the buoyant force is going to be equal to gravity times density times volume, which is gravity, which is gravity times mass, which is equal to the weight of the displaced fluid. So we can say here the buoyant force is equal to the weight of the displaced fluid. Or we can say the density of the fluid times gravity times the volume which is displaced. Either way, whichever is more convenient here. The weight of the fluid displaced might help to remember. If you remember it with this one, it might help to remember that it's just how much is displaced. So something like this. Okay, that's Archimedes' principle. The net upward force is equal to the weight of the fluid which it displaces. So there are circumstances on this. If something fully displaces, let's actually look at some of these pictures here. So like a submarine we have in figure B here, a submarine can actually change its buoyancy. It can take on water, it can release water, and it can change its weight, and so it changes its buoyancy, so it can go up and down in the water, the ocean. An anchor, although an anchor may rest, so in A here, although an anchor may rest on the bottom, doesn't mean that it doesn't experience a net buoyant force upwards. If we look at a free body diagram for this anchor, I'll just draw a box here, that it has a weight which acts down, mg, but it also has a buoyant force which acts up on it. And this is equal to the density of the fluid. So this is the density of the water times gravity times the volume displaced, which happens to be the volume of the anchor because it is completely displaced. Or it's completely submerged. So the entire volume of the anchor displaces fluid. but it needs a little bit more. The buoyant force is not enough to, the buoyant force is less than the weight. Because the buoyant force is less than the weight, this will create a net force downwards and it'll sink to the bottom, which is the point of an anchor anyway. So what happens once it gets to the bottom is that it needs an additional force, and we have a normal force. So with a complete free body diagram, we would say here the normal force from the seafloor up on the anchor plus the buoyant force minus the weight is equal to 0. Okay, and C, we have here in figure C with these balloons. Let's say that we have, we'll do a free body diagram for a balloon here. So free body diagram for a balloon, we would have, again, we'll just do a box. We have the weight of the balloon, which is relatively small, and it displaces a much larger area. So we have a much larger volume. The buoyant force here would be equal to, again, the density of this time it would be air times gravity times the volume displaced, which would be the whole volume of the balloon, because the balloon is completely submerged in air. And so the volume displaced would be the entire volume of the balloon. So the buoyant force is much greater than its weight. And so we have here buoyant force greater than the weight means that we're going to have a acceleration upwards, which is exactly what we see when you let a balloon go. It accelerates upwards, depending on what's in it. If you fill this with air, then mg becomes the same. It becomes heavy, and it doesn't actually accelerate up. If you fill this with something very light, like helium, then it accelerates upwards. So, yeah. So that's Archimedes principle and buoyancy.